Once again, I welcome you all to lecture number 25 of week 8 of the course. As a quick recap, in the last lecture, we started our discussion with the installation of rotating machines and the various type of routine test that is performed before commissioning of the rotating machine. Today, we will discuss on the installation and commissioning of static electrical equipment, that is transformer. Transformer plays a major role in electrical power system for transfer of voltage from one level to another and is termed as static electrical equipment. Based on the application, the two types of transformers which are commonly in use are known as distribution transformers, the transformers one used to see which is installed near to our homes, and power transformers which are installed in the substation. To ensure reliable power supply from a newly installed transformer, proper procedures during installation, testing, commissioning must be strictly followed. The key components of a transformer are: first, the diagram plate where the nameplate details along with the diagram of the windings of the transformer are given. Second comes the high tension and the low tension bushings. Then the core of the transformer, then comes the winding, that is the high voltage winding and the low voltage winding, then the tank body where the core is placed, cooling tubes and radiators, conservator, pressure vents, offload, onload tap changer depending upon the rating of the transformer, breather pipe with the dehydrating breather, oil drain valve, oil level indicator, earthing terminals and lifting legs. The other key parts of a transformer based on the specific site requirements are: if a transformer rating is more than 1 MVA, normally we used to have the Bucos relay, oil and winding temperature indicators, oil filter valve, marshalling box, high voltage and low voltage cable box, and best duct if it is required, where normally this best duct is provided on the LV side, and the rollers for the movement of the transformer. You can see the figure of a transformer, the picture of a transformer, where you can see the major parts, that is the conservator, the breather, the explosion vent in case if any short circuit take place in the windings of a transformer, and if the oil gets heated up and the vaporization of the oil take place, then without any major damage to the transformer, the vapor of the transformer, the oil vapor of the transformer can get out from the explosion vent. Then the bushings, the high voltage bushings, and if it is a transformer of high voltage ratings, then we have bushings both on the high voltage side and the low voltage side, the cooling tubes along with the radiators, the tap changers, it can be an offload tap changer or an onload tap changer depending upon the ratings, and the drain valves. The dispatch of the transformer from the manufacturing site in fully assembled condition depends on the transformer rating, limitation in transportation facilities, this handling facility at the installation site. In most of the cases, transformers cannot be dispatched as a whole unit and therefore has to be disassembled before transportation. Transformer dispatched as a complete unit, then it can be of three cases that can take place. Transformer dispatched as a complete unit, that means along with the oil, the entire transformer is dispatched as a complete unit. Transformer disassembled with oil filling to cover core and winding. The remaining portion of the tank body along with the conservator would be filled with nitrogen so as to prevent oxidation of the oil. No oil, the transformer tank body with core and winding filled with nitrogen and maintained at low pressure, normally at 5 psi. The nitrogen in the tank body is maintained so that the tank body should not come into direct contact with the air. For transportation of power transformers, one should use low bed multi-axle trailers so that the transformer weight gets evenly distributed over the entire transportation bed, so that we used to have multi-axle trailers when you used to transport transformers of rating more than 60 MVA. The detached parts are packed in separate wooden cases and are dispatched along with the transformers from the manufacturing sites. The parts that are packed in separate wooden cases are the bushings, the radiator with cooling tubes, conservator and drain valves, breather pipes and dehydrating breather, Buchholz relays, transformer oil in drums, because once you have removed all the oil from the transformer or partially the oil which you have removed, you have to keep it in drums and along with the rollers. The transformers, once it has arrived at the site, the following checks should be done. Cracks in the high tension, low tension bushings, or they have broken during the transportation, oil leakage from the welded joints, dents or cracks in tank sidewalls, cover, radiator fins, cooling tubes, conservator oil level side glass broken, loose bolts and clamps of the core, or if your transformer is filled with nitrogen, you have to check for the positive tank pressure for nitrogen, or if it is filled with dry air, you have to see that the positive tank pressure is there. If once the transformer is filled with either with nitrogen, which is an inert gas, or dry air. Following checks to be done before unloading of transformer from the transportation unit. Availability of access road between unloading point and the plinth. Foundation for transformer installation, whether it is already been done or not. Availability of mobile overhead cranes with adequate capacity to lift the transformer. Availability of wooden sleeper blocks of sufficient dimension for keeping the main transformer tank body above ground level, so that one can facilitate the jacking and fixing of the roller wheels. The unloading of the transformer is done by lifting the transformer tank body either by using wire rope of the appropriate size or polypropylene rope slings connected to the lifting legs provided on the side walls of the tank. From the figure, you can see that the lifting legs have been welded on the transformer tank side walls, and using mobile cranes, the transformer is lifted from the trailer. Unload the transformer on the wooden sleepers. Fix jacks of the required capacity at jacking pads. On the transformer bottom part, the jacking pads are given. So, you have to fix your jacks of the required capacity at jacking pads on all the four sides of the transformer. Ensure simultaneous operation of all the jacks. Once this has been done, once the transformer is lifted to the required height, connect the roller wheels which has been provided as a spare. Check the exact position of transformer so that the roller wheel groove sits exactly on the rail track, and then lower the transformer with the help of jack. Once this has been done, connect the wire rope of the winch to the towing hole of the transformer tank body and gradually haul the transformer tank body using winch onto the concrete foundation. Once your transformer has reached to the foundation, install transformer over a leveled floor base of sufficient strength to support the transformer weight. The transformer should be positioned on the foundation for easy access to read, operate and maintain the following as and when required. The first is the transformer nameplate rating. Then one should be in a position to easily operate the offload or the onload tap changes. Onload tap changes, normally we operate it from the remote access point, but if it is an offload tap changer, one should have clear access to operate the offload tap changer. Then the marshalling box or the control box of the transformer, so that if there is any electrical breakdown, one can easily check the wirings in the which are being terminated in the marshalling box. Adequate electrical clearances are to be provided from exposed live parts of the transformer to any earth point. Transformer should be well placed sufficiently away from all wall partitions to permit free circulation of air and also for movement of the maintenance personnel. Once the transformer has been placed on the foundation, rollers should be suitably clamped or locked to prevent any movement of transformer from its designated position. Power cables and control cables should be supported using supporting trays, angles and channels so that no pressure is exerted on the transformer bushing terminals or cable termination box. Naturally cooled transformers depend entirely upon the circulation of air to dissipate all heat generated due to internal losses, that is the copper losses and the core losses. Indoor installed transformers must be well ventilated so that heated air can escape and be replaced by fresh cool air. Necessary number of exhaust fans to be installed for heated air to escape. This installation of exhaust fan has to be done when your transformer is indoor mounted or indoor installed. So once your transformer has been installed, then the pre-commissioning check starts. The first is the mechanical pre-commissioning checks. Connect all the accessories to the main tank body, that is the high tension and the low tension bushings, the conservator, the Buchholz relay. In between the tank body and the conservator, the Buchholz relay comes, marshalling cable boxes, dehydrating pipe with breather, pressure relief valve, cooling radiators, oil and winding temperature indicators, and current transformers, depending upon the type of protection you are giving, whether it's a MERS price or a differential protection you are giving, or the over current protection you are giving, or the current transformers which are being used to measure the oil temperature. Use torque wrenches with proper torque setting for tightening or loosening of bolts. Ensure even fitment of gaskets. During assembly, ensure that all the gasket joints between radiator and the transformer tank are airtight and the flanges are evenly fitted so that no air should be in contact with the transformer oil. Ensure tightness of drain plugs available at the bottom portion of the radiator. After assembly of radiators, the shut-off valves provided at top and bottom should be opened because these valves are normally closed during the transportation from the manufacturing to the site where it has to be installed. The oil and winding temperature indicators shall be mounted vertically for best accuracy of the readings. So, you can see one of the accessories, that is the radiator along with the cooling tubes. So, one can see the air release plug which is there on the cooling tubes and the drain plug at the bottom of the radiator that is fitted to the cooling tube. The Buchholz relay is connected in the pipework between transformer tank and conservator. For correct operation of the relay, ensure the pipework on either side of the relay and the relay itself are all set at an angle of 3 degree to 7 degree with the horizontal. One has to see the arrow which is there on the Buchholz relay. The arrow shown on the Buchholz relay should point towards the conservator. Ensure the operating floats of the Buchholz relay are free. Ensure fitting of pressure relief valve, cable box and silica gel breather. Once the mechanical pre-commissioning checks have been done, one can start with the electrical pre-commissioning checks. Identification of faces over the cable box door for EC identification. One has to have a clear-cut identification of the faces, that is the red face, the yellow face and the blue face, which has to be labeled over the cable box door. Adequate cable support structure so as to ensure no undue strain on the bushing terminals in the cable box. No extra holes to be made in the bus bar at sides. Normally, the gland plates are given in the cable box but one has to see that only the number of holes that had been made at the manufacturing site that are required for the number of cables, only that should be there. No extra holes should be made on the gland plate of the cable box. The cables shall be clamped by suitable cable glands on the gland plate of the cable box. Once this has been done, check potential free contact terminals of pressure relief valve, Buchholz relay, oil and winding temperature indicator. Ensure the continuity of the control cable which has been laid for the pressure relief valve, for the Buchholz relay and for the oil and winding temperature, that the continuity is there from this points to the marshalling box for proper alarm and tripping functions in case of internal faults in the transformer. Check the continuity of the power and control cables from the online tap changer. The transformer tank body, cable box, marshalling box, etc. provided with earthing terminals should be permanently connected to the earth grid by means of galvanized steel flat that it can be 25 into 3, 25 into 4 or 50 into 6 galvanized steel flats one can use, or if the design requires copper flat, you can use copper flat or flexible copper conductors of suitable size. Ensure before connection the earthing terminals provided on the transformer to be clean from dust and paint, because normally when the transformer is being dispatched from the manufacturer's side, the painting of the transformer tank body along with take place. So one has to ensure that on the earthing terminal the paint should not be there, and one has to remove the paint before connection of the earth terminal, so that the proper continuity with the earth is there. Earthing connections with a good low resistance are essential for adequate protection against electrical faults. Once you perform the above electrical pre-commissioning checks, the condition of transformer oil should be checked before energization of transformer. The two main functions of a transformer oil are dissipation of heat generated from the winding, and second, it provides insulation between conductors having high potential difference, that is between the high voltage winding and the low voltage winding, and between the high voltage winding and the low voltage winding and the tank body, it provides the insulation. For meeting the above two functionalities, the transformer oil should have low viscosity so that it can dissipate the heat very fast that is being generated inside the transformer. Then it should have low volatility so that when the transformer oil vaporizes, that flashing should not, or no flare should take place. Then it should have high resistance to oxidation and high dielectric strength with minimum power loss or with minimum dielectric loss. For testing of this transformer oil, the oil sample has to be taken from the tank bottom and tank top. The sample should be taken in a clean and dry glass bottle with ground glass stoppers. So you have to take the oil sample, test it in a breakdown oil test kit, and you have to take at least 6 tests, 3 tests for the bottom tank bottom oil and 3 tests for the tank top oil, and then you have to take the average, and it should be more than 50 kV in standard test condition by maintaining the gap of the electrode as 2.5 mm. If the breakdown voltage is less than 50 kV for 2.5 mm gap, then one has to carry out the drying and purification of the transformer oil using the filtration oil filtration machine. Once if you find that the BDV test that the BDV voltage is more than 50 kilovolt, then one can go for the voltage ratio test. Apply 3-phase AC voltage through autotransformer on the high voltage side winding as shown in table, and the voltage ratio at all tap positions can be measured using suitable voltmeter connected to the low voltage side. So, this is the table for the voltage ratio test. So, one can see that the voltage applied on the high voltage side and the voltage measured on the low voltage side at different tap positions. The tap positions can be negative tap positions means minus 2.5%, plus 5%, then nominal tap, that is 0. Then the positive tap position indicates plus 2.5% and plus 5% depending upon the number of taps which are available in that transformer. Then you have to calculate the ratio obtained, and you can see that if there is any mismatch between the calculated value and the measured value, then there would have been a problem of the turns ratio. Then the next electrical pre-commissioning checks comes the magnetic balance test. The test is performed to check the imbalance in the magnetic circuit and also to identify interturn faults in the transformer. Normally, this test is performed because during transportation, the core bolts might get loosened, and therefore, the magnetic circuit, there would be a imbalance in the magnetic circuit. To see that whether such a thing would have happened during the transportation of the transformer from the manufacturing site to the installation site, the magnetic balance test is performed. Apply single phase 230 volt AC voltage between each high voltage phase, keeping low voltage open. Measure the phase currents of the transformer winding to which the voltage is applied and the voltage for other remaining high voltage phases, and record it in the column marked as double star and single star as shown in the table. So, what we have to do is that you have to apply the voltage. You can see that column 1 that we have applied the voltage between phase U and V, that is 230 volt, and then you have to measure the current in that particular phase, fine, and then you have to check the voltage of the other two phases, that is the other two phases which comes, that is your voltage of VW and WU. Similarly, you have to connect the single phase voltage between V and W, and similarly you have to connect the single phase voltage between W and U. So, what you can see that if there is any imbalance, that imbalance can be checked by measuring the phase current and as well as the voltages in the other two phases other than the phase to which you have applied the voltage. Now comes the IR test, the insulation resistance test. IR values of windings to earth between windings of high voltage and low voltage and between high voltage and low voltage windings shall be measured with designated insulation tester of suitable ratings, and readings should be noted. So, high voltage winding, what we can do? The note is that low voltage, all the low voltage winding, short it and connect it to the ground. Once this is done, measure the IR value between phase U and earth, where phase U is of the high voltage winding, and then between V and E, that is phase V and earth, then between phase W and earth. So, the measured value should be in gigaohms, and as I told you in the previous class, the minimum IR value should be 1 mega ohm per kilovolt plus 1. Once you have performed the high voltage, the IR test at the high voltage winding side, now we have to do the same test, the IR test at the low voltage winding side, by keeping the high voltage winding shorted and connected to ground. Then again the low voltage phase U to earth, then V to earth and W to earth. Then comes the next test, that is the winding resistance test. Winding resistance between phase winding should be measured using macro ohm meter. For distribution transformer, high voltage winding is connected in delta and the low voltage winding is connected in star. You can see from the figure that the high voltage winding is connected in delta and the low voltage winding is connected in star. And therefore, here also you have to perform the winding resistance test for different tap positions, that is U to V, V to W and then W to U for different tap positions, starting from the negative tap positions followed by the normal tap position and the positive tap position. Similarly, you can see that my winding on the high voltage side is connected in delta. Therefore, the measured value is given as X, that is between U and V. I measured the value, the resistance value using macro ohm meter, it is coming as X. Similarly, between V and W, it is coming as X, and between W and U, it is coming as X ohms. And the calculated winding resistance value, that is the per phase value, should be R is equal to 1.5 into X, because it is connected in delta. Therefore, the per phase resistance value, that is R, should be equal to 1.5 into X, and if there is no interturn shorts or no loose connections, then all the phase values of the high voltage winding, all the resistance phase values should be same. Now, once you have done this test on the high voltage side, that is the winding resistance test, you can do it for the low voltage side. The low voltage side, because it is a star connected winding, you can measure the phase resistance directly, that is between phase U and the neutral point N, between phase V and the neutral point N, and phase W and the neutral point N, and the measured values you can see that R, R, R and R. Fine. Or if we are measuring the phase resistance between U and V, that is between the two phases UV, VW and WU, if the neutral is not available, then the measured values comes to be Y, that is between U and V it is Y ohms, between V and W it is Y ohms, and between W and U it is comes to Y ohms. Then the calculated winding resistance, that is the per phase resistance, R is equal to 0.5 into Y, R is equal to 0.5 into Y, R is equal to 0.5 into Y. The last column resistance value, that R should match with the R which is coming in the third column. But normally if the neutral point is given, then you can directly measure between phase and the neutral point. That means the phase resistance one can measure directly if the neutral point is given. Then comes another important test, that is the vector group test. The vector group test of a transformer checks the phase sequence and an angular difference to ensure its correctness with the given specification. Transformers within the same vector group can be easily paralleled if they meet other conditions that are required for parallel operation. The classification of a three-phase transformer according to the vector group are YY0 and DD0, where the capital letter Y stands for the high voltage winding connected in star. The small y, that is the small letter y, gives that is the low voltage winding again connected in star, and the phase difference between the high voltage phase and the low voltage phase is 0 degree. Similarly, DD0, where D stands for the high voltage, capital D stands for the high voltage winding connected in delta, small d stands for the low voltage winding connected in delta, and again the phase difference is 0. Similarly, you can see the second one, that is YD1, stating that the high voltage winding or the primary winding is connected in star, the secondary winding is connected in delta, and the phase difference between both of them is 30 degree. That means the low voltage phase winding is leading the high voltage phase winding by an angle of 30 degree. Similarly, YD11, where again the low voltage winding is lagging the high voltage phase winding by an angle of 30 degree, and the last one is YY6, that means again the low voltage winding is lagging the high voltage winding by an angle of 180 degree. That means both the high voltage winding phase and the low voltage winding phase are 180 degree or out of phase. Procedures for vector group test. Consider the transformer vector group as DY11. That means the high voltage winding is connected in delta, the low voltage winding is connected in star, and the low voltage winding is lagging the high voltage winding by an angle of 30 degree. It indicates the primary winding is connected in delta, secondary winding in star, and the secondary phase voltage lags the primary phase voltage by an angle of 30 degree. The winding connection and the phasor diagram, you can see it is clearly given in the figure. Connect 1U and 2U. That means the phase U of the high voltage winding, where 1 shows that it is in high voltage winding and 2 shows that it is in low voltage winding, and 1U, that means the phase U of the high voltage winding and the phase U of the low voltage winding, you have to short it. Then apply 3 phase voltage to the high voltage winding phase 1U, 1V and 1W. Once we have given the 3 phase voltage, you can give it from an auto transformer. Measure the voltages between 1U and N. You can call that voltage as VUN. 1V and N, we can call this voltage as VVN. 1U and 1V, we can call it as VUV. 1V and 2V, that means the phase V of the high voltage winding and phase V of the low voltage winding, we can call it as V1V, 2V. 1V and 2W, that means the phase V voltage of the high voltage winding and phase W of the low voltage winding. We call this voltage as V1V, 2W. 1W and 2W, similarly 1W and 2V with their designation as given. If the vector group dy11 is there, then the voltage VUN plus VVN should be equal to VUV. Similarly, the voltage V1V, 2V should be equal to V1V, 2W. Similarly, the voltage V1W, 2V should be greater than V1W, 2W. Once this inference is correct, then we can definitely say that the transformer vector group is dy11. Once this pre-commissioning electrical checks have been performed, we have to go for additional checks before transformer energization. All high tension and low tension connections are tight and secure. All the accessories are operational, that is the oil temperature indicator, the winding temperature indicator, the Buchholz relay where you have got the alarm and the trip, the pressure release valve, the cooling fans if it is an oil natural air force based transformer, the space heaters normally in winter conditions, limit switches, etc. All the oil shut-off valves and radiator valves are open and draw valves are closed. All thermometer pockets are near filled with 85% of oil. All radiators are completely filled with oil. Correct level of oil in the bushings and conservator. Check the color of the breather, which should be blue for silica gel, and after that earthing connection for main tank, neutral bushing, marshalling box, control gearbox, the cable box, arcing horns, etc. are correct. After that, no excessive strain on the bushings and termination bus bar. That means the cable support structure should be intact. Arcing horn gaps for bushings are correctly fixed. The spacings are correct between the horns. All CT secondary are connected to the measuring and protection circuit. No CT secondary should be kept open. Otherwise, the high voltage on the secondary side can take place and it can damage the CTs. Therefore, you have to see that the CT secondary should not be open. Release air from the air release plugs of main tank, inspection covers, radiator, conservator, Buchholz relay and its pipeline. You can do this by tapping on the transformer tanks. Bushing should start from the bottommost point going upwards, covering all air release plugs. Energize the transformer at no load only and check for any abnormalities for the next 8 hours. Once you have convinced that all the airs have been released from the transformer main tank body, the conservator, the Buchholz relay, and wherever there is a possibility of the air getting trapped, that trapped air is removed, you energize the transformer at no load and check for any abnormalities for the next 8 hours. On satisfactory operation of transformers at no load, load the transformer up to 50% for the initial 4 to 8 hours and then gradually increase your load up to the rated load. This is the transformer nameplate is given there. So, you can see that on the left hand side the tap numbers, where tap number 1 stands for plus 5%, 2 stands for plus 2.5%, the 3 is the nominal or the 0%, tap number 4 stands for minus 2.5% and tap number 5 stands for minus 5%. So, you can see which type of transformer, the vector group, you can see that the high voltage winding is connected in delta, the low voltage winding is connected in star with the neutral out, and the phase difference between the low voltage and the high voltage is 30 degree. That means the low voltage winding phase is lagging the high voltage phase by an angle of 30 degree, and the type of cooling is oil natural, air natural, and you can see the losses on the and the weight of the transformer. The weight of the transformer with oil and without oil is specified so that it can help you during the unloading or loading of the transformers. And on the top side one can see that the high voltage level, which is 11 kV, and the low voltage, which is 415. That means the nameplate detail of a distribution transformer is given. The rating of the transformer is 100 kVA, and you can see on the right hand side the basic insulation level which is given, and other details are given. Actually, the nameplate detail is just like the birth detail of a human being. I think we have covered all the required procedures and all this as a part of the transformer installation and commissioning. Please go through the lectures. If you have any doubt, you can ask in the next class. Happy learning. Until then, bye.